We are now recording. I'll try to get the current slide open. I know at least one of you, maybe more. How many of you are Lawson students? Dan, you are. You're the only one. Are you a Lawson student? All right, good, great. I don't know if you know Miss Nyla Gerasi. She is one of the math instructors, mostly on the Birmingham campus. She is also the coach of the math team, Lawson State math team. Sorry, you guys, you can't participate if you're not a UAB student. And they are meeting every Tuesday from 4:30 to 5:30 in the science building on the Birmingham West campus in room C100. They're preparing for math competitions next year, but they are also having a good time as a club and a team. So if any of you Lawson students, and if you know of any others, you don't need to be a math major, but preferably people who have taken or are taking calculus, those are most appreciated because that's what most of the competition is based on. And then this is for all of you. I'm not really sure why we're doing it, but they sent it for us to announce. Because this is a private company, and I really cringe a little bit advertising for private companies. But the name of the company is STEM Jobs. Okay? STEM, of course, science, technology, engineering, and math. And these are, this company has released a new tool to connect classrooms to careers. The STEM Type Navigator allows students to match their interests to opportunities, they say after high school. I would think after college would be more appropriate. But anyway, this is a Pittsburgh company, and they're trying to connect students to opportunities, blah, blah, blah. So, from post-secondary institutions. Okay, so why do they say high school when it's post-secondary institution? If you'd like to read this, find out more information, supposedly it's a really easily navigable device. You can find the jobs out there that probably would fit your particular interest the best. So it sounds like a good deal. I just can't speak anything for the company. But if you're interested, I've got the information up here. Please take a look. All right. Any questions on anything we've done so far, math or otherwise? Okay. We're at the top of page 184. Chapter 3 is applications and differentiation. 3.3 is increasing, decreasing functions, and the first derivative test. And that's what we'll be doing in example 2. So if there are no questions, let's proceed. Find the relative extrema. Now, of course, relative extrema means relative maximum or relative minimum. This doesn't mean absolute, this won't include endpoints. These are going to be interior points only. Relative extrema of this function. F of x is equal to 1/2 x minus sine x in an interval from 0 to 2 pi. And notice they even put this as an open interval, which means, of course, you wouldn't be considering the endpoints anyway. Okay? For absolute extrema, you usually would, but you couldn't if it's an open interval. So, how would you suggest we proceed? And maybe before we start, remember the two things that have to be true about looking for extrema on an open interval. Two things. Continuous functions, polynomial functions are continuous, and sine and cosine functions are continuous, smooth, continuous, differentiable everywhere. So that hits everything. Continuous and differentiable on the open interval. They're smooth, continuous, and differentiable everywhere. These two are, but you have to have it on the interval of interest, and certainly that fits. So, with that meeting the criteria, what do we do now? Go back to sleep. No. What do we do now? Find the derivative, always a good first answer in this course. Let me get my pen set up. I forgot to do that. Okay. So, what is the first derivative of that function? 1/2 is the first part. Minus cosine x. Okay. Now, I actually stated something a little bit incorrect before. I said the functions had to be smooth, well, continuous for sure. Smooth and differentiable are nice on the interval, okay? But that's not quite required, okay? Because to find the relative extrema, what two conditions do we consider? Especially having taken the first derivative. Hint. Why did we take it anyway? Because it's a good thing to do?
Because it has a slope.
Say again?
Because it has a slope.
Because this gives you the slope of what slopes are we interested in for extrema on an interval. Say again? Vertical. Okay. That certainly is one that we're interested in. That would be where the first derivative does not exist. Or, what's the other condition? Anybody? That's undefined. Where the first derivative does not exist is undefined. Vertical tangents, yeah, that all means the same thing. What's the other condition? Where the first derivative is equal to 0. Oh, how did you guess that? Okay, where the first derivative is equal to 0. Now, is that undefined anywhere? On this interval or anywhere else? No. Cosine is defined everywhere. 1/2 is defined everywhere. It's defined everywhere. So there are no vertical tangents, no places where the first derivative doesn't exist or is undefined. So we go next to what? In fact, this is what I would consider first. What? Plug what in? You first set it equal to 0. First, the first derivative is equal to 0. That is a potential extrema. Doesn't guarantee it is, but that's a potential one. Okay? What do you do with that? Help me.
Move the cosine over.
Okay, add cosine x to both sides. It must be a Monday today or something. So I'm going to reverse sides here and do cosine x is equal to 1/2. And the question is, where is that true on this interval? Where is cosine x equal to 1/2? Pi thirds, you're absolutely right. And where? 2 pi thirds cosine would be negative. So pi thirds from 0, that would have a cosine equal to 1/2. And where else is cosine positive? The first and the fourth quadrant. So down here, same value except down here, where is that? Take it, 5/3 pi? Absolutely right. So there are the two positions where where the first derivative will be 0, where cosine is equal to 1/2. Pi thirds and 5 pi over 3. Okay. Now, that's all it said. Oh, wait. We really do need to get, because these are points, we really need to get the coordinates for those points. These are the x coordinates. What is the y coordinate when x is equal to pi thirds? Anybody know? Well, you plug in pi thirds here. Okay, it would be 1/2 times pi thirds minus what is Yeah, sine of pi thirds, you're right. Okay, I didn't hear what you said. Sine of pi thirds. Okay. And what is 1/2 of pi thirds? Pi 6, pi over 6. And what is sine of pi thirds? Square root of 3 over 2, is that what you said? Okay. Sounds good to me. And that's a really bizarre number, isn't it? And you really can't make it much nicer. You could multiply numerator and denominator in that last term by 3 to get it all over 6 and make it pi minus 3 root 3 over 6. But there's no real reason to that. That just makes it maybe a little easier for typesetting. I don't know. Okay, how about the other one? 5 pi thirds. Okay, what would that be? F of 5 pi thirds, 5 thirds pi. What would that be? 1/2 of 5 thirds pi minus the sine of pi, 5 thirds pi. This again would be 5 pi over 6. What would that one be? What's the sine of 5 thirds pi? Okay, that would be 11/6 pi would be negative 1/2, or 7/6 pi. Sine would be 1/2. Sine, not cosine, sine of pi thirds, or 5 pi thirds. The y value is a bit further down than 1/2. Yeah, negative square root of 3 over 2. So it's negative, so that makes this a plus the square root of 3 over 2. And if you did the same thing to that as we did before, which you don't have to do, multiply this by 3 and that by 3, then you have 5 pi minus 3 root 3, no, plus 3 root 3 over 6. You don't have to write it that way. You could just write it the way it was. Let's see how the book wrote it. Oh, they didn't do it. Shame on them. They just put down those values. Okay? And the first one was not very far down the other. So, sorry we went to all that effort. They just found the critical numbers. They didn't actually evaluate it, which the extremo is an XY pair. I mean, it's a point. It's not anything else. But they didn't do that, so I guess you wouldn't either. Okay, they should have asked the question, what are the critical points? All right, less clear my writing. Anyone need that any longer? Okay, let's see how they do it. Note the f is continuous. That's the first thing it's got to be on the interval 0 to 2 pi. Therefore, you take its derivative, and the first derivative is 1/2 minus cosine x, exactly like you did. Then what do we do with it? Two conditions we look for on that derivative, either places where it has vertical asymptotes, doesn't exist, not defined, they all mean the same thing. That would be the first case. That's defined everywhere. And secondly, where it's equal to 0. So that's where we go next. To determine the critical numbers of this interval, set f prime equal to 0. Okay? So that's what we do here. Add cosine x to both sides and switch sides, and you have cosine x is equal to 1/2, and then find those two values, pi thirds and 5 pi thirds. Okay. Is it Alexis? Taylor. Okay, sorry. I did forget one other, I don't know if this is a major announcement or not. But, okay, I guess I should have included several things here to make sure y'all realize this, though I'm in little doubt that you did. But, you know the good news, bad news situation of this week, right? Okay. There is no class on Wednesday. That's the bad news, right? Now, I'm not going to say that our administration is anal retentive or anything, but because the 4th of July is a holiday, they emphasize to us that gives us 8 hours off for the 4th of July. Okay? So because we work 10-hour days in the summer, we owe them 2 more hours this week. So what I'm doing, I'm staying an extra 40 minutes today, Tuesday, and Thursday. So my office hours, we're not at all, I know we're lieutenant, no. But, therefore, I usually have office hours from 2 to 6 on Mondays and Wednesdays. Today I have office hours 2 to 6:40. And then Tuesday and Thursday I'll be on the Birmingham campus, East Campus, and usually my office hours there, because I'm stuck there in the afternoon. Class ends at 4:30, 5:30, usually 5:30 to 6, but now it'll be 5:30 to 6:40. Birmingham East Campus, the Ethel Hall Nursing Building, I'm in room, whatever, the K103 or whatever, it's the 103, just shortly after you come in the door. So if you need me Tuesday or Thursday, 5:30 to 6:40. Okay. So anyway, I don't know why I happen to think of that now, but anyway. So there's our solutions. Those are the critical numbers. Because there are no points for which the derivative does not exist, you can conclude those are the only critical numbers. And then we didn't do that, did we? I forgot that. They didn't say to do it, but let's do it. We should do it. Find the relative extrema. We need to determine, so let's go back. Oh, I've already erased it all, sorry. Okay, yeah. Did any of you happen to write down what those points were? Pi thirds, and it was pi minus 3 root 3 over 6, and the other, is that right? And the other was 5 pi thirds and 5 pi plus 3 root 3 over 6. Okay. Now, what we didn't do was determine whether these were maxima, minima, or neither. Remember, these, just because they have a first derivative equal to 0 doesn't mean they're an extremum. That would be a maximum, this would be a minimum, this would be a neither. Tangent of 0 here, but it doesn't, it's increasing on this side, increasing still on the other side. So it may not be an extremum. Okay, that said, what is happening to this function? Remember our original function? F of x is equal to 1/2 x minus sine x. Okay? What is that function doing? Well, the 1/2 x is sort of taking off like this, right? But the sine x is doing this stuff, right? So what the 1/2 x is, it provides the envelope, positive 1/2 x minus 1/2 x, inside which 1/2 x, if y'all remember back probably in pre-calculus or somewhere back in your past, you had what they call damped periodic functions. Now, I hope you didn't leave off the p in there, but never mind. The damped periodic functions, and what that does, it's doing like this, okay? Always going up and down because it's a sign, wherever I wrote it, but the envelope is getting bigger, within which it goes up and down. I think of this as no, I'm sorry, that's not quite true. That would be if it was 1/2 in front, 1/2 x in front. But it's still that type of a thing. The sine function is going up and down along the 1/2 x, okay? But it's still going up and down. It's not taking off and not coming back. So these are, by the way, relative maximum or minimum, because it goes up and down and up and down. Now this is not how they do it. They don't think through it this way. What they do is test some values. So let's do it that way. Let's test. Give me something to the left of pi thirds. It's easy to test. Something to the left of pi thirds is easy to test. Zero. All right, good. Yo. Okay, don't work too hard here. That would be 0, and what sign of 0? Say it? 0. So that would be 0. So the left here at 0. Here we have a number. I think it's pretty easy to tell that's less than 0, right? It's a negative number. Because root 3 is about 1.7 or so. 3 times that is going to be something greater than 3. Like greater than 4. Greater than 5, probably. Okay, somewhere in that thing. So that's negative, and this is 3.14. So this has got to be negative. Not very negative, but it is negative. So you start at 0 and you're going down. So far, this looks like it might be a relative minimum. Okay? Now, they'll do a point in between these two. But why? Just do this point. Look at that. That number is quite a bit, yeah, very positive. This is positive, that's positive, the whole thing's positive. So if this is slightly negative, that's slightly positive. No reason to do a number in between, because it's a continuous function. It's got to be a continuous function, so this has to be a relative minimum. Now, all we have to do is to determine if some number greater than 5/3 pi is going to give us something positive or negative. Well, think of a number to the right of 5/3 pi. An easy one to evaluate.
7/4.
Say again?
7 pi.
Okay, pi fourths. Is that what she said?
7 pi 4.
7 pi fourths. Okay, that's the one they used in the book, didn't they? Yeah, okay, good. It is one that's out there, okay? It's to the right of that, 7 pi fourths, okay? It's just short of this is pi third short of 2 pi, that's pi fourth short. So yeah, that's greater than this. So let's look at that. That would be 7 pi fourths here. That makes it 7 pi eighths this term. And sine of that would be root 2 over 2, negative root 2 over 2. So then you have to evaluate, you pull out your calculator and do what we just said, 7 pi over 8 plus, because it's minus and minus, the square root of 2 over 2. Okay, that's a lot of work. Okay, but do it. I mean, hard work isn't bad for you. Okay, do that. What do you get?
Say, you want to do 2 pi?
Second?
I was going to say, do you just want to do 2 pi instead?
Yes, I'd rather do 2 pi if that's okay with you. I'm way too lazy to do something that hard. Let's do 2 pi. Okay? That's to the right of it. Okay, I know it's not in the domain, but who cares? It's a continuous function that still works. Okay? So let's do 2 pi. What is the sine of 2 pi? 0, right? Okay? And what is 1/2 of 2 pi? 1/2 of 2 pi is pi. Okay? That's 3.14 blah, blah, blah. Okay? I think we've already determined this is way beyond 3, right? A very large number. Okay? because this is pi over 6 would be about 1/3. 5 times that would be 5/3, and that's more than, no, it's not quite, but then you add this to it, and you're up there, okay? So this is less than that. So that has to be a relative maximum. Relative minimum, relative maximum. But frankly, to me, you can tell that just by the nature of the function. It's going up and down like this, climbing up the 1/2 x line here. Sine is going up and down, so it's got to be the relative maximum or minimum. That's the minimum. That's the maximum. Okay? So we did do their part. I forgot to, sorry. So let's go back. And they chose well, they did it another way, which is fine too. They looked at the first derivative. They looked at the first derivative to the left of that point, and pi 4 certainly does there. And the first derivative there was negative, meaning it's going downhill there. And then they looked at pi right in the middle of it, okay, between those two. Yeah, right in the middle. And they looked at that, and there your first derivative was positive. So it went from negative, 0 to positive, absolute minimum. Relative minimum, okay? And so we got it increasing in the middle, and then we looked at the right-hand side, and they used the 7/4 pi, and all they did was evaluate the first derivative there, and found out it's decreasing again. It's negative again. So it's positive on this side, 0 at the point, and decreasing. That means it has to be a relative maximum. Relative minimum here, we got it the same way, similar, but this is called the first derivative test rather than using the function values, which to me the function values, well, because you had that x in there, it probably did make it a little more complicated. So all you have to do is find out positive or negative here. You don't have to figure out whether it's less than or greater than. So this would be a little bit easier. Okay? Sorry, I didn't see that coming. Should have. And let's see, did you show the graph? Yes, here it is. At pi thirds, you see you do have a relative minimum. And they chose a value here showing your first derivative was negative here, 0 there, positive there. You're fine. Okay? Positive here, 0 there, negative at this value. Yeah, you know it has to be a relative maximum. Okay? First derivative test. Since you already got the first derivative, it's already worked out for you. Yeah, go on and plug that in, and that would be easier than going back to the original function. Okay. Any questions? All right, that is the last slide on the set, which means none of the others are going to be up here. So let's do the other. Example 3. Find the relative extrema of this function. F of x is equal to 2/3 times x squared minus 4 to the negative 1/3 times 2x oh, I'm sorry. I'm looking at the wrong part of the problem. Okay. Sorry about that. I was not looking at the problem. Start over. I was looking at the first step. I thought they usually rewrote the first step, but they didn't. F of x is equal to x squared minus 4 to the 2/3 power. All right. Now, what is required to begin with is this a continuous function? What you're thinking on? Yay or nay? That's all that's required for you to do the first derivative test. Is it a continuous function?
Except for when x equals 2.
Well, okay, except for when x equals 2. When x equals 2, this becomes 0. 0 to the 2/3 power. That's 0. So I don't think it has a problem there, because this is the cube root of that thing squared, right? The cube roots are defined everywhere. Square roots are not. Cube roots are. Okay? You're thinking well, though, because that's the next step that's going to give us a problem. But this is defined everywhere. They didn't give us an interval, which I kept looking for. In fact, that's how I saw I was writing the wrong thing down, because I couldn't find the interval anywhere. So this is on all real numbers, but remember what a cube root function looks like. It looks basically like this. Okay? That's what it looks like. This is just doing some other things to it, but still defined everywhere. So, defined and continuous everywhere. What you reckon our next step is? Take a derivative. Sounds like a winner to me. F prime of x is equal to what? Come on now, that was last chapter. 2/3 x squared minus 4 to the negative 1/3 times 2x. Perfect. There's your derivative. Okay. Now I'm going to clean it up ever so slightly. Okay. What's that? Okay, good question. Okay, let's start from the beginning. The power rule says you take the exponent times the coefficient. That's what 2/3 times 1 is 2/3. This thing to this, subtract 1 from that. But then you've got this thing. There's your interior function. The chain rule says then you take the derivative of what's inside there. So that's where it comes from, the chain rule. Second? Yeah, because this is x squared minus 4. Okay? If that had been just x, then there would have been a 1 on the outside, which you wouldn't have used. Okay. Whatever you have inside here, whatever you have, you take the derivative and put out here. Okay, if this had been x cubed minus 15x, you can't do much with it, but you take the derivative of that and put it out here. Okay? Chain rule. Okay? Now, you don't need to do this, but to me, it's easier to see if you clean it up just a little bit. And here's how I mean that. 2 times 2x is going to be 4x over 3, but this negative 1/3 power moves it downstairs and makes a x squared minus 4 to the positive 1/3 power. Okay? Now, if I'm taking a derivative, leave it in this form, or at least something close to it. But if I'm trying to evaluate it, which is what I'm going to do, that form helps me see what's going on better. Okay? And what are the two conditions we look for in our first derivatives? Help me out.
We want to see if it's continuous.
Second?
To see if it's continuous.
Okay. We've already seen that the function is continuous. The first derivative doesn't absolutely have to be continuous, but usually it is if the function is continuous. But, no, that's not quite true. If it's absolute value function, it would be. But this is not that, okay? But what are the two things we look for in that first derivatives? Where it's equal to 0 would certainly be 1. So let's set this thing equal to 0, and what would make that true? What values of x would make that true? Okay? Here's an easy way to look at it. This is a 0 over here, right?
Can you take that volume and multiply it?
Okay, yeah. I wouldn't do that much work. I mean, it will work that way. But, yeah, if you multiply both sides by this denominator, 3 times that would be 0, this times that would be 0, and then what do you have left?
The 1/3. 4x.
4x equals 0. What values make that equal 0? Second?
0.
X equals 0. Very good. Now you can think through that, and it's perfectly fine. How I like to look at it, this is a fractional form, and that's equal to 0. Now how can a fraction ever be 0? If the numerator is 0. Doesn't matter what the denominator is. If the numerator is 0, the fraction is 0. Unless, of course, the denominator is also 0, which is indeterminate then. But this is not. Okay? So yeah, where x equals 0. So there's one critical value. X equals 0. Okay? Ding, ding. What's the other thing? And that's the only place where the first derivative is equal to 0. What's the other thing we have to consider? Okay, we're going to get there later. We're still looking for critical values. Two conditions for that first derivative to determine a critical value. Last problem, you jumped all over the second one and left off the first one. This one, you jumped all over the first one and are leaving off the second. Wait, second.
The y value?
That may have something to do with it, but what's the condition for your first derivative? What two conditions do we look for? Where it's equal to 0 or? You said it last time. It's the first thing that came to your mind. The other condition for your first derivative. Either where it's equal to 0 or where it is undefined, exactly. And where is this first derivative, right here, written this way, where is that not defined? Say again? You picked up on it before we even did the derivative. Say again? Okay.
X equals 2.
Okay, where the denominator is 0, is that what you said? I hope so. Please say yes. Okay, yeah, that's what I said. Okay. Where the denominator, well, where this is either where the first derivative is undefined, does not exist, has a vertical asymptote, whichever you want to say. You said all three of those before, and that occurs when that denominator is 0. Okay? And what makes that denominator 0? 3 will never be 0.
2.
Say again?
The 2 is 2 minus -2 or plus 2.
Exactly, where x is equal to either plus 2 or minus 2, that goes to 0. Your derivative does not exist there. So those are the other two values. X equal -2, x equal +2. Those are your three critical values. Okay? Now, and this is on all real numbers. So all we have to do now is determine what f prime is to the left of -2, in between -2 and 0, in between 0 and 2, and to the right of 2. So we got 4 test values to make. You pick the value. Give me something less than -2. Less than -2. -3. Is that what you said? Yeah. -3. Okay? So let's take that and plug it in our first derivative here. What's your numerator become? -12. Okay? So we're doing f prime of -3. That would be -12 over 3 times. And what do you get when you square a -3? 9 minus 4 is 5. Raise that to the 1/3 power. Who cares what you get? The answer is it's positive, right? 3 times a positive number is going to be positive. The numerator is negative, so this thing is less than 0. Do you buy that? Okay? I'm going to work this out. 5 to the 1/3. It doesn't matter what the value is. We're looking for the sign of it. That's what makes the first derivative test a little bit easier to do. The numerator is negative, the denominator is positive. That makes the whole fraction negative. So, to the left of -2, we're negative. At -2, it's not defined. Let's look to the right of -2, but between -2 and 0. Negative 1 sounds like a winner to me. Okay? So f prime of negative 1. What would the numerator be? Negative 4. Denominator is going to be 3 times. And what do you have when x is equal to negative 1? X squared would be? That would be a negative 3 to the 1/3 power. Now, the first question that pops to my mind, can you take the cube root of a negative number? Yeah, sure you can. Square root you couldn't, cube root you can't. Any odd index root you can't. And what will it come out be? Negative. And negative over negative is? Positive. So guess what, team? This is greater than 0. So here you had something with a negative slope coming into negative 2, undefined slope at negative 2, but positive coming out. Okay? What we have there, vertical asymptote like you noted before, but coming in on this side, going out on that side, that is a relative minimum. Exactly. So x equal negative 2 relative minimum. Okay? Negative coming in, positive going out, that makes that negative. I mean, a minimum. All right, we already have f prime at negative 1. We need something to the right of 0, but less than 2. 1, so let's do f prime of 1. What does the numerator become? What does the denominator become? 3 times negative 3 to the 1/3 power, which is negative. We don't care what the value is really, it's negative. And positive divided by negative is negative. So here coming up to 0, you're increasing to the left, 0 here, and now decreasing there. So that makes this a decrease. Okay. It's increasing here, positive first derivative to the left of 0, 0 at 0, and then a negative first derivative to the right of 0. That makes 0 a yeah, it sort of is, but what are we looking for? Maxima or minimum. What would that be? Maximum, of course, okay? So this would be a relative max. Okay. Now, we already have 1 evaluated. That's the left of 2. Now we need to look to the right of 2. What might we choose? 3. So let's try 3. Let's put it up here. F prime of 3. That's going to be a numerator of 12. Denominator of 3 times 5. The cube root of 5. And guess what that is? We don't care what the number is. What's the sign? Positive. Okay, for sure. So here we have, coming up to 2, we have a negative slope. F prime of negative 1 is less than 0. Vertical asymptote there because it's not defined. And to the right is positive from there. So that makes this a minimum, relative minimum. So x equal to relative minimum. Okay. All right. I'm not going to draw the function for you, but here it is. Ooh. Okay. It's negative coming in. The first root is negative coming in. Undefined at x equal negative 2. And we didn't. This time, they didn't actually have us do the values. They should have. I mean, we could have. We did them last time. They didn't ask for them. Now, I didn't do them this time, and they are sort of looking for them. The point at negative 2, the function value there at negative 2, this would be 4 minus 4 is 2/3. That raised to the 2/3 power is still 0. At positive 2, same thing. At 0, this would be the cube root of 16, which I don't know what it is, but some positive number, okay? So they'll probably tell us in a minute. So we have our points that we're interested in. I can hold this in place now. Coming in at 0, it stops, and then the first root is positive, so it's increasing after that. Relative minimum here, up here, and they just let it the cube root of 16. They didn't evaluate it. That's something between 2 and 3. Okay, because cube root of 8 is 2, and the cube root of 27 is 3. So something between 2 and 3 is the relative maximum. And coming down here, negative slope, negative first derivative coming in, undefined there, positive going out. That makes sense. Minimum at relative minimum at Q0.
So does it give us the numbers to plug in, or we choose our own numbers?
What's that?
Does it give us the numbers to plug in, or do we choose our own numbers?
You choose your own, just choose wisely. Okay? As in everything else you want to choose wisely. Okay?
We know where to start.
Okay.
We always start with 0.
Okay. Now, you find the critical values, right?
Yeah.
Okay. So here we found our 3 critical values. The ones to choose something to the left of the least, that's that -2. Anything out there would do. -3 million would have been all right. I wouldn't have chosen it, but you could. -10. They chose, y'all chose -3. Good, small, easy number to evaluate. Okay? Now, all you're interested in is what is the sign of that first derivative there. You found out it's negative. So that means it's decreasing coming in. Okay. You found these. These are fixed. Now you do something between this one and the next one. Line them up. -2, 0, 2. So find something between -2 and 2. -2 and 0. -1's an obvious choice. So that's why he chose that. Okay? And then you know what it is at 0. It's first derivative is 0 there. It's positive to the left, negative to the right. Stand up, sit down, fight. No, I mean, that's your maximum way. Okay? So it's a negative. That's what we got here. Oops. Here, okay. Negative at -1. And choose something to the right of 2. You choose. Anything will work. Y'all chose 3. Good choice. When you put 3 in there, you'll find out the first derivative is positive there, negative here, undefined here, so it must be a relative number. You choose based on those. That defines an interval for you. Do this if it helps. Draw your number line. Okay? Here is 0, here's -2, here's +2. Those are your 3 critical points. Choose something to the left of 0, something in between here, and to the right. Left of -2, in between the next 2, and something to the right of that. You choose anything you want to in that. -1/2, +1/2 would have done for these. Perfectly fine. Anything you want to choose in there. But make sure it's left of -2, between these 2, between those 2, to the right of that.
Alright, we got 4x over 3 times x squared minus 4 to the 1/3 equals 0. Alright, that's what I'm saying. How you find your critical number out there?
This right here.
Yeah, I see how you got that. I understand how you got that, but how did you get 0 from that?
Okay. You're looking for 2 things. For that first derivative, this is your first derivative, right there, first derivative. I rewrote it this way. I said, where is it equal to 0? So that's what I did. It set it equal to 0. Well, it doesn't matter what the denominator is doing. The only way to get this equal 0 for that numerator to be 0. The only way to make that happen is x equals 0. So that gave me my first critical form. Okay? Now, overstate it a little bit. If x equals 0 made the denominator 0 at the same time, that's indeterminate. We can't deal with that. But it didn't. That made this some other number. Okay? So yeah, we're fine with that. In fact, that made the number. You need it for later. For x equals 0, this will be -4. No, plugged in here. Yeah, but you don't need this part. But this would have been -4 to the 1/3 power, which is some negative number times 3. Doesn't matter what the first derivative is there, as long as it's not got a zero in the denominator. In the numerator, that's zero. Okay. Now, that's all the places where the first derivative is zero. The other two is where this first derivative does not exist. And that's what you look at the denominator. Okay. Good question. Great question. All right. Any others on example 2? Okay. Let me clear this then if y'all got it. Everybody got it? And also, time for a commercial break. I did receive this morning the 3rd paper. This class is surging to the lead in the number of research papers turned in. Yes? You choose your topic. Anything that has to do with calculus. That's what we're studying. You can choose something that was fair to your major, something you're interested in, anything to do with calculus. People, theories, whatever. You choose it, find the material, write on it.
How long is that?
What's that? 1 to 2 pages. That's double space, word processed. Okay?
MLA?
Say again?
MLA? Format?
You choose your format, but just stick with it. Once you choose it, don't be varying. Okay? Okay? I don't impose anything on you except be consistent. Okay? All right. And while I'm on that topic, whatever, I received a couple of tests in today. Now, I didn't check to see whether they're test 1 or test 2, but hint, hint, you've had test 1 for several weeks now, and I'm still missing 1, 2, 3, 4, 5 of those. Now, those may have come in this morning. That would be great if they did. That means I'm still missing 2 of them, 3 of them. So please get test 1 in, because you already have test 2, and guess what? I've received 1 test 2 in already, folks. So please be working on test 2 as well. It's not due yet, but be working on it. Okay. It may be due, but whenever. Okay. So let's move on to example 3. Find the relative extrema. Oh, we just did example 3, didn't we? Yeah, I'm sorry. Example 4. Yeah. Was there a question? Okay. Example 4. Here's something special about example 4. Wait. There's a little bit of verbiage before they do the example 4. Let's hit that. Notice that in example 1 and 2, the given function is differentiable on the entire real number line. We noted that. For such functions, the only critical numbers are those for which f prime is equal to 0. Oh, 1 and 2. Okay, yeah. Example 3, though, you had the others for which it was not defined. We already talked about that. But it says, when using the first derivative test, be sure to consider the domain of the function. For instance, and this next example will show this, so I'm not going to get into it. This is what the problem is. Now, here's something about this problem. You can go to larsoncalculus.com for an interactive version of this type of example. So go there. If this is fuzzy to you, go there. They'll explain it better. Here's the function. F of x is equal to x to the 4th plus 1 over x squared. And all it said is find the relative extrema of that function. What's the requirement before you even start the first derivative test? The function must be continuous. Is this function continuous everywhere? Say again? That's an x to the 4th up here and an x squared down here. So it's going to be like a parabola, kind of, a little bit in some ways. But what's the problem here, Houston?
X cannot be 0.
X cannot equal 0. Why? This function isn't even defined. Okay? Not even defined. Okay, you might say, well, it's indeterminate. No, it's not. That would be 1 over 0 when x equals 0. So it's absolutely not defined. So you cannot have any interval that it contains 0. So you can look at this from negative infinity up to 0, but not including 0. You can do it from 0 to positive infinity, but not include 0. You cannot have an interval that includes 0 at all, ever. So, this function, you have to do that, and that's usually when I write down in a function like this, first thing I'm going to do is x not equal to 0. If they don't do it for you, you put it in there. You cannot have x equals 0. Now we can proceed. Okay? Now, here's a really good, clever first step. Okay? Rewrite this function. Divide x squared into x fourth, and what do you get? X squared. And what you have left is plus 1 over x squared, right? Now, even better than that is to write it x squared plus x to the minus 2. I always prefer to have no variables in the denominator. Now, Nolan loves to use the quotient rule, so he could have done it without doing this, and it is perfectly legal. But I prefer not to have anything in the denominator, any variable in the denominator, if I can help it. If I can't help it, I'll use the quotient rule. And I don't want to have any negative way. That would mean changing this to a negative x. I do this before I take a derivative because it makes it easier. Because what are you going to do? Once you know what your function is, what's your next step? Take a derivative. Okay? Remembering, x can't be 0, so you got to be on one side or the other. So what's f prime of x? And what would that be? 2. Wait. Not 2. 2x minus 2 x to the, a little louder, negative 3. Perfect. Okay? Now, what two things must we consider here of that first derivative? Now, here, I think it's easier to go back to the form that's maybe you think in better. That would be 2 in the numerator. Well, let me just write it. 2 minus 2 over x cubed, which I would write as, you don't have to do this, but I think it, well, that's fine. Just leave it like that. That would be perfectly fine. Okay? Now, two things we're looking for is where, once you find that first derivative, what two conditions are you looking for? Anybody? Where it's undefined, or where it's equal to 0. I want to get them both out there before you forget them, okay? Where it's undefined or equal to 0. Well, certainly it's undefined where?
0.
X equals 0, but you can't have x equals 0. So that's out of the picture now, okay? So now all we're looking for, that's the only place this would be undefined. And that you can't have because it can't be 0, okay? Now the other thing would be where this thing's equal to 0. So set that equal to 0. And how would you go about solving that? Huh?
I like how you wrote the first way up.
This one right here?
Yeah.
Okay, go with it.
I would have factored after I did it.
You would have
I
what?
would have factored that way.
Okay, how do you factor it?
I would have took out 2.
2.
I would have said 2 equals 0.
Second?
I would have said 2 equals 0, and I would have said x minus x. So
Okay.
third.
X minus 1 over x cubed, is that what you're saying? Set that equals 0, is that right?
Yeah, you were right like that.
Or are you rather write it the other way?
Yeah, I read right.
Okay, let me get it the way you want it. I mean, you're the boss here, okay? Minus x to the 1/3, is that right? I mean, x to the minus 3? Is that how you want it?
Yeah, I just said both on equal 0.
Okay. And guess what? 2's never going to be 0, right? So I'll just divide that away. So, same thing here. So we have x minus x to the minus 3 equals 0. Now what would you do? Subtract. How about, that's okay. Let's just add x to the minus 3 to both sides. Okay? Is that all right? Okay. So now you have x is equal to, and can I please go back to the other form? Equal 1 over x cubed. And what does that suggest you can do? Say again? How? How about multiplying both sides by x cubed? That will get rid of your denominator. I don't want to get rid of x. I want to get rid of the denominators. And what does that give us?
X
Equal 1. There, finally. What values of x would make that equal to 1? Second?
Just one.
Second?
Just one.
1 will certainly work. And negative 1 will work. Okay? So either x equal 1 or x equal minus 1. Those are your two and only two critical values. You want to have 1 to the left of 0 and 1 to the right of 0. Okay? So guess what? We cannot cross and have it equal to 0. So you will have one relative extrema to the left of 0, 1 to the right. You cannot have 1 at 0 because the function's not defined at 0. Okay? So what are we going to have to choose? You know your first derivative is equal to 0 there. And the first derivative is not defined only at the place where the function is not defined, so that's out of the picture. So these are your only two critical values. What are you going to have to do to them? To determine what the relative extrema are. They neither one may be relative extrema. We don't know. How will we determine? How have we been determined? Something to the left, something to the right of each of those. Guess what we can't use? 0. Don't give me a 0 to use. Something to the left is negative 1. You choose. Negative 2. Okay? And we're looking at the first derivative there. And let's go back to our first derivative. Okay? All right. Now, I really don't care which way you write it, but let's do a negative 2. That'd be 2 times a negative 2 minus 2 over negative 2 cubed. Okay? Well, 2 times negative 2 is negative 4. And this is going to be negative also. Negative here, negative there. That's going to be plus. And this 2... once you're taking care of the signs, this 2 will take out one of these and leaving a square. That's 1 over 1/4. Okay? Now, I don't care exactly what the value is. I want to know what the sign is. What's the sign of that? Negative. So the left of negative 1, you're negative. So f of negative 2 is less than 0. F of negative 2, of negative 1 is equal to 0. We need something to the right of negative 1, but not 0. Okay? Something between negative 1 and 0. 0.5 sounds good to me. Okay? Let's do that then. First derivative would be 2 times 0.5 minus 2 times 0.5 cubed. Okay? Well, 2 times 0.5 is 1 minus 2 over, oh, and that's a minus 0.5. Whoa. Yes, sorry about that. It's a minus 0.5. Sorry about that. That's a minus 1, and this will be a minus 0.125, okay? Right? And minus over minus is plus. So this is going to be a negative 1 plus a number. Okay. Now think of this. This is basically 1/8, right? Right? This is 1/8. 2 over 1/8 would be 2 times 8 over 1. 2 times 8 is 16. This is very, very positive. So over here it's negative, there it's 0, and to the right of that it's very positive. So F, goodness gracious, this thing is aggravating. Okay. And F of negative 1/2 is very positive. So guess what negative 1 is? If it's less than 0 coming in, the negative slope coming in, 0 at negative 1, but positive going out, guess what negative 1 is? Negative slope coming in, 0 here, positive slope going out, guess what that is? A minimum. So F of negative 1, or x equal negative 1 is a minimum. Okay? Now we need to do the same thing for plus 1. The only thing is we can't use negative 1 to the left of it. Why? It's the left of 0. You can't include 0 in the interval. So you have to take something to the right of 0, but left of positive 1. 1/2, 0.5. That's what you chose before. It'll make the calculation easy now. So F of 0.5, that's what I was starting to do before, that's equal to 2 times 0.5 minus 2 times 0.5 cubed. Okay? Well, again, this is 1. This will be a minus 2 over 1/8. That's how I like to do it. So that would be a minus 16. That's going to be very negative. So F of 0.5 is very negative, right? And we know that F of 1 is equal to 0. That's your critical value. Now we need something to the right of 1. 2, okay? So let's do F of 2. I'm running out of room. F of 2, F prime of 2, that's what we're looking at, F prime, sorry. F prime, okay. F prime of 2 would be 2 times 2 is 4 minus 2 over 2 cubed, okay? So it'll be 4 minus 2 over 8, which is 1 over 4. What's that? I don't care what the value is, it's, what's the sign?
Yes, positive.
Positive, okay. So F, goodness gracious, I got carried away on my signs here, symbols here, okay. And F prime of 2 is positive, greater than 0. So what does that make 1? Okay? If your first derivative is negative coming in, 0 here, and positive going out, guess what that is? It's a relative minimum 2. Can they both be? Yes, they can. Both are relative minimum. And here's why. clean place to put this. I'll do my best with it right here. If you were to graph this negative coming in, first root is negative, 0 at negative 1, and it is at negative 1, 2. We didn't calculate it. We could have. That would be negative 1 to the fourth would be 1 plus 1 is 2 over negative 1 squared is 1. So that would be 2. Negative 1, 2. Positive 1 would also be the same thing. 1 plus 1 is 1, 2. So here are the two relative minima. Undefined up here, so don't even go there. But they're both increasing as we get close to 0. This is decreasing here, increasing there, relative minimum. Decreasing here, 0, and increasing there, relative minimum. Both of them.
Wait. Did you say x to the fourth?
Say again? X to the fourth plus 1.
So why below did you put x squared?
That's the function. That's what they gave us. X to the fourth plus 1 over x squared. Oh, pi here?
Yeah.
We divided this into that and gave us x squared. This into that is that.
Okay.
Yeah. It just makes it easier to. You wouldn't have done that. You would have done right to the product group, quotient group. I know you wouldn't have even messed with that. I understand. So you don't have to worry about it. Okay. All right. Both of them work perfectly well. So that was example 4. There is a thing at the bottom of the page on technology. You're certainly welcome to take a look at that. And there's one more, example 5. Surprised they don't do that one. And they don't even have it at larsoncalculus.com. Can I erase? Okay. So here's example 5. The path of a projectile. Pretty nice looking jump shot there, right? Neglecting air resistance, the path of a projectile that is propelled at an angle of theta degrees is this. Y, which usually is going to be the height, is equal to minus g. Anyone have a clue what g is? Acceleration due to gravity. Okay. Secant, what a fun trig function. Secant squared theta divided by 2 v0, that's the initial velocity squared, times x squared, that would be the horizontal displacement, plus a fun old tangent theta, that's the angle of incidence again, times x, and that's plus h. Okay. Now this is only good for 0 less than, they say are equal to 0, theta, less than or equal to pi halves. And frankly, folks, I find that slightly obnoxious, okay, for this reason, okay? We're talking about the path of a projectile, okay? Sure, it will work if theta is equal to 0, okay? But if theta is equal to 0, it's going to go downhill. There's not really any interesting value in that at all, okay? Now, here's what I really thoroughly object to, equal to pi halves. That is not defined at pi halves, and that's not defined at pi halves. For by all means, this should be, remove that equal sign there. In fact, I'm going to do it, okay? I can't believe they put it there in the first place. But the function is not defined at theta equal to pi halves, so don't include it. And for all practical purposes, it doesn't make any sense for theta equal to 0. If you shoot it straight out, it's just going to go down. I mean, going to follow a parabola, but it's not going to do very much. It won't be a good basketball shot. Unless, of course, you're dunking it, okay? And then an angle of 0 is going to be fine, okay? But if you're doing a jump shot, unless you can get well over 10 feet up where you release it, yeah, then you could release it there. I don't think many of us can do that, okay? I know I can't. Okay. Where y is the height, x is the horizontal distance, g is the acceleration due to gravity, V0 is the initial velocity, h is the initial height. Okay? That equation is derived in section 12.3. If you're interested, go there. Okay? We're going to let g be 32 feet per second per second. So we're going to let g equal 32 feet. The shortcut of saying that is per second squared. Okay? And we're going to let our V0 be 24 feet per second. Our V0 equal 24 feet per second. And our h equal 9 feet. Okay? H equal 9 feet. Okay. What value of theta will produce the maximum horizontal distance? The maximum horizontal distance. Huh. Interesting. Okay? All right. How they begin here is just go on and plug in these values up here. So this will be y is equal to minus 32 secant squared theta over 48. That's 2 times, oops, no it isn't. Okay. Sorry about that. I wasn't paying attention. 2 times 24 squared, V0 squared, x squared plus tangent theta. They didn't give us an, they're looking for that, okay? X plus 9. Okay. Now, still a very messy problem. It says, what value of theta will produce a maximum horizontal distance? Okay. Now, let's first clean up our numbers a lot. This 24, by the way, is 2 times 2 times 2 times 3, right? 8 times 3, 24. This 32 up here is 2 times 2 times 2 times 2 times 2. 2 times 5, right? By that? Okay. That's 32 is 2 to the 5th power. Right? Now, if you're squaring this, you're going to double every one of those. So not just that, it'll be times 2 times 2 times 2 times 3 again. Okay? Now, to clean up things a little bit, let's divide out some 2's. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So what does that leave us with here? A minus secant squared theta x squared over 4 times 9 is 36. Do you see that? You didn't have to do it the way I did it, but I just thought that might be one way to do it. Plus tangent theta x plus 9. Okay? That's what your y is equal to. All right. Now their question here is what value of theta will produce the maximum horizontal distance. Okay? Now, it says to find the distance the projectile travels, let y equal 0. Now, why would that be true? Okay? Now, what you're doing here, if you think about this, and they show shooting a basketball, and that's not a bad thing to do because these things are about right. 32 feet per second, that's acceleration due to gravity. You can't avoid that. 24 feet per second, I don't know if that's the average speed at which a basketball goes, but whatever it is, it's some speed. Okay. The reason this is fairly reasonable is height of 9. So let's say you are 6 feet tall, maybe a little bit better, and your arm length, when you shoot the basketball, you're up here, so let's say that's another 1.5 feet, okay? So 6, that'd be 7.5, and if you get a 1.5 feet off the ground, you'll be at 9 feet. I can't get a 1.5 feet off the ground, so that's going to rule me out, but that would be something reasonable, okay? So at time t equals 0, that's where the ball is, 9 feet in the air, okay? Going at 24 feet per second, and falling at 32 feet per second squared, because that's got a minus sign in front of it, okay? Now, how far it travels is when the ball hits the ground somewhere over here. Well, that's at y is equal to 0. So that's going to give you your maximum horizontal distance when y is equal to 0. Okay. Now, we've taken up this much room and haven't even started solving the problem yet. So let's start over, and let me write this at the top. Our new problem is now this. I'm going to change signs everywhere at the same time too. I'm going to move y is equal to 0, so set this equal to 0, and then change the signs of both the others, multiplying or dividing by -1. So here's going to be our new problem. Secant squared theta x squared over 36 plus tangent theta x plus 9 is equal to 0. Okay, that is the function that we're starting with. All right. Now, I really don't like that one either, but that's about the best we have to live with. Okay. Now, I was starting to do it one way, and then I realized we haven't covered that yet. So we can't do it that way. So forget what I was thinking. You couldn't think it anyway. Here's how the book proceeds, which is perfectly legitimate. I'm going to erase all this down here. We're just going to go with the upper part. Okay? I sure hope I copied everything right. Okay? Pretty sure I did. Okay? We've already plugged in the values, so we don't need this anymore. We don't need our simplification anymore. So let's get rid of all this stuff. Okay? And that was what we wrote over at the top. Okay. So there's our equation. All right, now the book did it this somewhat strange way, which is perfectly good, okay? Let's consider that a quadratic equation. You okay with that? So it's a really weird one, but it's a quadratic equation. In fact, I'm going to rewrite it. Is that all right? This will be secant squared theta over 36 x squared plus tangent theta x plus 9 equals 0. Okay? Now, if we want to solve that quadratic equation, any one of you want to tackle factoring it? Please, if you want to, do it on your own time. Okay? We don't have time now. So if you can't factor, what do we usually use? Can't factor a quadratic equation, what do we usually use? Say again?
I mentioned how
What? What do we use? If you can't factor, how do we solve one? Quadratic formula. How does that go? Okay, let me write down. If it's ax squared plus bx plus c equals 0, we say x is equal to minus b plus or minus what? B squared minus 4ac all over 2a. Okay? Now in our case, here's the a, here's the b, and here's the c. So, what would be our x here? Negative tangent theta plus or minus the square root of tangent squared theta minus 4 over 36, right? Okay. C is 9, right? All over 2 times A, and there's your A. So that will be secant squared theta over 18, right? Because 2 times that makes it 36 into an 18. Good deal. Okay. Now what magical thing do you see here? 4 times 9 is 4 times 9? 36 over 36 is 1. So this gives you this minus tangent theta plus or minus the square root of tangent squared theta minus secant squared theta. Does anyone know what that happens to be? Good old trig identity. Over secant squared theta over 18. Anyone remember it's called the Pythagorean identity. It doesn't show up in that form, but it has those values in it. Anyone remember it? Huh? Okay. If you go to the, I'll derive it for you, but I think it's actually easier to go to your front inside cover, that first page inside the cover. Oh, you don't have your books. Let me go. Okay. Hopefully you remember this Pythagorean identity, right? Sine squared theta plus cosine squared theta is equal to what? 1. 1 and only 1. Okay? Now if we want to get tangents and secants out of there, divide everything by cosine squared theta. Cosine squared theta over cosine squared theta. You get something? Okay, I heard something. Okay. What's sine squared over cosine squared? Help me. Tangent squared theta. Okay, there's a tangent theta. Cosine squared over cosine squared. 1. Equal 1 over cosine squared. Second? Secant squared, right? All right, now all we have to do is subtract the secant from both sides and subtract the 1 from both sides. And what does that give you? Tangent squared theta minus secant squared theta is equal to a negative 1. Ooh! Bad news, bears. You can't have a negative 1 there. Oh, wait. No? You know where I messed up? Sorry about this. When I went in and multiplied by minus 1, that wrecked the whole deal here. Okay, I was supposed to leave that minus sign in there. Yuck. I thought it was just going to make the problem easier.
Could you change?
Well, no, what I did, I forgot to change these signs. I changed the first, but didn't change the next two. Did I? That was supposed to be this and that. I just changed the first sign. That's where I messed up. Okay, So that'll be a plus tangent here. And that will be a minus 9 here. And that'll be a plus here. Now it works. Okay. Forget Pythagorean identity. Okay, sorry. That was not the way to go. Okay. I can't believe it's not, but it's not. Okay. Because you can't get that out of your Pythagorean identity. So what you have to do is change this to sines and cosines. That would be sine squared theta over cosine squared theta plus, let me erase these others because we're not going to use them anyway. Sorry about that, folks. Okay. All right. Plus 1 over cosine squared theta. That's what we've got, this expression here. So that's sine squared theta plus 1 over cosine squared theta. Okay. All right. So what our new x is, this is really taking way too much time. This is sine theta over cosine theta plus or minus the square root of sine squared theta plus 1 over, and square root of cosine theta is cosine theta. Okay, and that's over 1 over 18 cosine squared theta. Okay, 1 cosine theta can wipe out one of those. And that leaves us with sine theta plus. Now, let's just right now say, to get the maximum distance, don't use the minus sign. Okay, that's what we're looking for, the maximum distance. Minimum distance, that would get you something behind you if you use the minus sign. So use the maximum. Plus the square root of sine squared plus 1. And this is all over 1 over 18 cosine theta. Okay? Which would be 18 cosine theta times this thing, sine theta plus square root of 1, sine squared theta plus 1. Okay. Now that's what they leave it as. At this point, you need to find the value of theta that produces maximum value of x. Applying the first derivative test, okay, by hand would be very tedious. So they say use a calculator. Well, why didn't we just use one to begin with? You could have graphed that whole function using a calculator and then found the maximum value. So why did they take us through all that mess to get there? Okay? And they say it's going to be greatest for about theta equal 35 degrees. So my word, what a pain in the neck problem to do all that to us. It said, but to do this by hand would be really tedious, so use a calculator. Well, guess what? Give me a calculator to begin with, just enter the whole problem and go through that, but never mind. All right, I'm sorry I wasted your time on it. 3.3, remember, CalcChat, okay. The answers to odd numbers are in the back. They're at calcchat.com for tutorial help and worked out solutions to the odd number exercises. And then a few of these are also at calcview.com. So homework, do number 3. That's the only one like that. It's at calcchat.com. Do any of the odds 5 through 9. They're all at CalcChat. 5 is at CalcView. Do any of the odds 11 through 17. They're all at CalcChat. 13's at CalcView. Do any of the odds 19 to 39. They're all at CalcChat. 21's at CalcView. Do any of the odds 41 to 47. They're all at CalcChat. 41's at CalcView. Do any of the odds 49 to 53. They're all at CalcChat. None of them are at CalcView. Do 55. It's at CalcChat. Do any of the odds 57 to 61. They're all at CalcChat. None are at CalcView. And then exploring concepts, if you're interested in these. They're not bad. They're pretty decent look. Do either 63 or 65 if you choose to. And then you can do 67 and 69 if you'd like. Okay? I would say do 71. There's a think about it 73, so I would definitely think about that problem. 75 is a pretty good applied problem. 77 is a reasonably good applied problem. 79 is definitely a good applied problem. And then you can do either 81 or 84. They're not that bad. 85, probably use the graph for that one, and I think you'll be able to pretty much estimate your answers. 87 and or 89, either one of those or both if you'd like. They're at CalcChat. All these odds are at CalcChat. There's true false, 91 to 95. They should be at CalcChat as well, probably in the back of the book as well. 97 and 99 are both proofs. If you wanted to try those, you certainly can, but you surely don't have to. Okay? And then there's a section project here on even 4th degree polynomials. If you want to look at that, you can. I don't think that's anywhere at CalcChat or anywhere else, but you can if you want to. All right, I think we're through with with section 3.3. Sorry, I wish I hadn't even gotten into that last problem. When I first read the problem, I knew exactly how to solve it, and then I thought, wait a minute, we haven't done that in this class. We've done it in our Cal 2 class, but not in this one, so that's where I had to start doing it the way the book did, and then wound up, nothing worked out well. And it said, so it's going to be really tedious, use a calculator. Man, if you got that, use a calculator to begin with. Okay, going to start this one from current slide. I didn't think. How are we doing time-wise? Okay, and we go till 10:40. You want to? This is a good break place if you want to take a break. You want to? I don't mind getting up and running to the restroom. So let's do a pause right here at the break. Okay. Continuing in application of differentiation, we're now moving to 3.4, which is talking about concavity and the second derivative test. Whereas 3.3 was increasing, decreasing functions and the first derivative test. So obviously something else we're going to be able to measure with the second derivative. So let's move on to the objectives. We'll determine intervals over which a function is concave up and downward. Now, number one, do we know what concave up and down means? You do? Okay, good. If not, we're going to define those terms first, okay? And then determine intervals, okay? We'll find any points of inflection, and that's going to be a point where it goes from being concave down to concave up, or concave up to concave down, okay? We'll define what a point of inflection is. And we'll apply the second derivative test to find relative extrema. So the same thing we were doing before with the first derivative test, we're now doing with the second derivative test, which frankly is so much easier. So that's one reason I tend to just want to skip over the first derivative test, but it is a doable thing. And it wasn't hard. The second derivative test is just easier. So let's start with, what in the world is concavity? Okay? Now, you've seen that locating intervals on which a function is increasing or decreasing helps to describe the graph. In this section, we'll see how locating the intervals on which f prime increases or decreases, not the function, but the f prime increases or decreases, can be used to determine whether the graph is curving upward or curving downward. That's concavity. Okay? So here's the definition of concavity. If f be a differentiable function, okay, now to be differentiable, remember, it must be continuous. Okay, absolutely. You can't take the derivative of a discontinuous function. Don't even bother. Not only must it be continuous, it must also be smooth. So now, absolute value problems and things like this, where you have points or cusps, those are out of the question. The f be differentiable on some open interval I. The graph of f is concave upward on I when the first derivative is increasing on the interval, concave downward on I when f prime is decreasing on the interval. Okay, so we have that. I still don't have a mental picture of what concave up and down is. So let's see if they'll give us one. Here's one. They say the following graphical interpretation of concavity is useful. Let f be a differentiable function on open intervals. Got to be. That means smooth and continuous. If the graph of f is concave upward, then the graph of f lies above all of its tangent lines. That's not how I think of it either, but it's certainly true. Okay? If it's concave upward, that means the first derivative is increasing. Here the first derivative is slightly negative, even less negative, so it's increasing. Even less negative, even less negative. Down here it's 0, so it went from being negative to 0, that's increasing, right? And then it's more positive, more positive, more positive, more positive, more positive. Well, that's concave upward. F prime is increasing. But notice here the tangent lines here are there, there, and there. The function is always above them. Concave upward. Okay? Now, do I use either of those when I'm picturing what concavity is? No, I look at this and say, if that was the mouth of the cave, it would be facing up. The cave is down here, right? Concave up. Okay? That is up. Okay? Now, concave down, the first definition said the derivative is decreasing. First derivative is decreasing. Here, the first derivative is slightly positive, less slightly positive, so it's decreasing, less slightly positive, less until it's 0, which is decreasing, then more negative, more negative, more negative, more negative, so that's one way. Okay? Or that the graph lies below all of the tangent lines. Here's a tangent line, here's a tangent line, it's always below it. There's another way to look at it. Or, if this is the mouth of a cave, you know, it's facing down. To me, that's how I do it. Concave down. Okay. Now.
Could you just say a parabola, like going upwards, it's just concave up and a parabola?
It certainly is, but you see, you have shapes that are not parabolic. But if you picture a parabola, anything shaped like that, yeah.
Split it in half and basically split it like that.
Yes, exactly.
Like that.
That's exact, and that's pretty much how I think of it. I think of a parabolic shape, even if it might not be a parabola. You're absolutely right. That's a good way to look at it.
The concave down with much as convex.
Yes.
Concave and convex.
Okay, if you're looking from above, it would be convex, but then that to me gets sort of confusing. But if that's how you see it and that's how you understand it, go for it. Perfectly fine.
Like this way.
Okay.
Just like concave up, on, down, and like
Good way. Perfectly good way. All right? Was that high school or college? College. Good deal. Okay? And that's I'll leave it up there till the end. I just don't want to leave it up too long because it dries out on the board and then it's hard to erase like this. That's why that stayed up there over the weekend and I can't get it. I've got to get Windex and clean it up. Okay, I'll try to remember. Okay. Now, to find the open intervals of which a graph of a function f is concave up or concave down, you need to find where the intervals on which it's increasing or decreasing. Now remember, that's really the key, whether the first derivative is increasing or decreasing. And what tells you whether something is increasing or decreasing? Is derivative. So you take a derivative of a derivative, what do you get? F2 prime, yeah, F prime, the second derivative of F. Exactly. So here's if you're looking at the graph of f of x equal 1/3 x cubed minus x. Okay? Here's what they say. It is concave downward on blah, blah, blah because, well, here's what you do. Take the first derivative. Let's do that. What is the derivative of that function? What's f prime?
3x squared.
Whoa, let me get my pens back. Sorry. Okay. F prime of x, I can't write, is equal to, say again?
3x squared.
Isn't it just x squared?
Oh,
It's 1/3, yeah. Yeah, x squared minus 1. Okay? And then go and take the second derivative. F double prime is 2x. Okay? So, it's where the second derivative is positive. And where is that positive? Any values x that are positive. X 0 up is negative anytime x is 0 down. Okay? So it's concave downward on the open interval from minus infinity to 0, concave down there, and concave up anywhere past that. Okay? Now, if you drew the graph of that function, which I'm glad they did and I didn't have to, then what you have is your picture there, concave down everywhere here, concave up everywhere there. And the turning point is at 0. X equals 0. Well, look at the second derivative. This is the graph of the, well, this is the graph of the first derivative. It's a parabola shifted down, negative second derivative here, positive second derivative there. So sure enough.
Would negative 1 on that first graph, would that be the max?
Right here?
No, on the graph.
Okay. Here.
Yeah, would that be your relative max? No. Yeah.
Here?
No, negative 1.
Negative 1. Yeah, right. Yeah, right there.
Would that be your relative?
Relative maximum, relative minimum. Okay? Now, because you see the first derivative is positive here, negative there, 0 there, so that makes relative max. Negative here, positive there, 0 in the middle, that makes relative net. But you're hitting on something really good here. If your concavity is down, it has no choice but being a max. If the concavity is up, it has no choice but being a max. Just like your vertex on your parabola is a relative minimum, is absolute minimum or maximum, depending on the sign of that first term. Okay? So, you see we get lots of really good stuff by considering the second derivative. You don't need to do all your interval tests anymore. That's why it sort of drove me crazy to have to do them. But if we get to this section faster, we wouldn't have had to do it at all. Well, it doesn't hurt to do it. Okay? So, similarly, the graph of f is concave upward on the interval from 0 to positive infinity because f prime is increasing everywhere on that interval. The next theorem shows how to use that second derivative of the function to determine the intervals on which the graph is concave up or concave down. So here it is. If f is a function whose second derivative exists on an open interval. Now what does it mean for the second derivative to exist? The first derivative must be smooth and continuous, meaning the function has to be smooth and continuous, okay? So here we got a little bit more strict thing that not only does the function have to exist, the first derivative has to exist, and the second derivative has to exist. So if f double prime of x is greater than 0 for all x's on some interval I, then the graph of f is concave upward everywhere on that interval. If f double prime is less than 0 for all x's on some interval I, then the graph of f is concave down. Positive up, negative down. That sort of tends to make sense. You have to remember there is concave up results in a relative minimum, and concave down results in a relative maximum, if there is one there. Okay. So to apply this theorem, 3.7, first locate the x values for which f double prime is equal to 0. Okay? Or f double prime does not exist. What does that sound like? It sounds just like the first derivative test, only now we're doing it with the second derivative. Use those x values to determine the test intervals, and finally test the sign of f double prime in each of the test intervals. Okay? So, let's do an example. Determine the open intervals on which the graph of f of x equal 6 over x squared plus 3 is concave up and concave down. Now, what you reckon you have to do first? Take a derivative, always a good possibility of being the right answer, okay? Now, my question to you, how do you want to take the derivative of that? I know how Nolan does. How do the rest of you want to take it? And either way is perfectly fine. There's nothing wrong with either way. How would you take it?
Is the product rule going to be easier?
Second?
I'm saying, is the product rule going to be easier? Or should we just use the
product.
Not the product rule, it's the quotient rule.
Yeah, the quotient rule is the one I know that you like to use. Whether you do or not, I'm going to say that. How you can use, here's what I'm saying. How you can use the product rule here, which frankly I found a little easier, is to rewrite this as 6 times x squared plus 3 to the minus 1. Okay? So you can use it just like it sits here in the quotient rule, rewrite it like this in the product rule. And it really doesn't matter. Which way do you want to do it? Quotient rule. Okay, do the quotient rule. What is f prime b by the quotient rule? Say again?
It's going to be x squared plus 3
X squared plus 3
times 0 minus that's going to be 2x plus.
Okay. Don't you have to do the numerator? High 6 times 2x. Is that right? If you're going to do the quotient rule, do it right, okay? Over what?
X squared plus 3 squared.
Right, exactly. Okay, so this will be minus 12x over x squared plus 3 squared. Okay? Now, just to do it the other way, the f prime here would be minus 6 times x squared plus 3 squared times 2x. Right? which basically gives you the same thing, minus 12x over x squared plus 3 squared. Okay? Both ways give you the same answer. Okay? However, did you see this coming? You've got to take a second derivative too to determine concavity, right? And in that case, you've got to take a second derivative. In this form here, which is what you get from the quotient rule, you almost have to use the quotient rule again, whereas this form lends itself to the product rule. Don't go as far as doing that. Stop at this point. I just took you there to show you it's the same thing. But let's use the product rule there, or the quotient rule here, either one, which you want to do. Quotient rule, I figured it. Okay? So down here we'll do f double prime of x is equal to, and what would that be?
That'll be 2. No, I'm sorry, I was doing the G back. X squared plus 3 squared. Times, and that's going to be just 12,
Negative 12.
Minus
negative 12x.
You do the chain rule?
Yes, you do.
Okay, so that's going to be 2 x squared plus 3 1.
To the first power, got it.
And then it's going to be 2x over x squared plus 3 to the 4th.
Okay. You asked for it, you got it. Toyota, there it is. Unsimplified, but you can deal with it. Okay, let's clean it up a little bit. That'll be a minus 12 times x squared plus 3 squared.
Before you do anything, okay. I was going to see, is there any way you can get rid of like one of those x squared plus 3?
That's exactly what I was going to do, but I wasn't sure you'd see it if I did it earlier. So let me get the eraser to work, okay? I like that way of thinking because I want to get rid of them as much as possible. Here we have one up here. Get rid of one of those and get rid of one of those and make it a 3. Yeah, very nice. Okay, so that would then give us a minus, so this is still just working. That would be minus 12x squared minus 36 minus plus, yeah, I'll make that a plus. That would be,
24x?
second?
Would that be 24x?
I can't hear you.
24x.
Yeah, but I was going to do more than that. 2 times 2 is 4 times that would be 48 x squared. Yeah, that's it. Plus over x squared plus 3 cubed. Okay? And combining those together, you get 36 x squared minus 36 over x squared plus 3 cubed, which would be 36 times x squared minus 1 over x squared plus 3 cubed. There's your second derivative. Okay? I hope. Oh, goodness, I hope. Okay? It said determine the open intervals on which the graph of that function there is concave up and concave down. Where will this be concave up? Where the first derivative is?
I mean, just look at if it's increasing or decreasing.
Second?
Which is look where it's positive and negative.
Positive and negative. Okay? And it will be concave up where it's positive. So where this thing is positive, which means this is positive, that's positive, right? X squared plus 3 is always positive. Q that is always positive. So it's just where this is positive. Well, this is positive anytime x is greater than or between minus 1 and 1, right? That's where that's positive. No, backwards. Outside of that, outside of negative 1 and greater than positive 1. Because in between this is negative. So this will be positive from negative infinity to 1 and from 1 to positive infinity. It's concave downward where this is negative, and that's only when x squared is less than 1. Then it's going to be negative. So you can look at that and sort of reason it out then. Okay? Now, did you want to see using that way? Product rule, see if it's any easier than this, or you'd rather not face the truth? Okay. Huh? What's that?
I'm always going to do the quotient.
Yeah, so why bother? Okay, so, but actually, to do the product rule with that is not bad either. Neither one of them are bad. Okay? It just, I think, saves a step or two, but that's all. All right, so that's what we determined. Let's see what they determined. Okay? Begin by observing f is continuous on the entire number line. Okay? We didn't do that. We probably should have. Why is that continuous everywhere? Because our denominator is never negative. Is never 0. Who cares if it's negative? It's never 0. Okay? Definitely never negative either. Never 0. Okay? So therefore this is defined everywhere on the real number line. Okay? Next. Okay. Find the second derivative. Well, guess what? You got to find the first derivative first. Uh-oh. Look at how weird they were. They changed it to this so they could use the power rule. Okay, not even the product rule, the power rule. Okay? And when they took derivative, when they wrote it this way.
That's the chain rule.
Huh?
Isn't that the chain rule?
Yeah, you're going to use the chain rule, but it's also, the reason I call it the power rule, you got a power here. Negative 1 times 6 times this to the minus 1. Then you do the chain rule. Yeah, it involves the chain rule as well. Okay? And that you get that, which you can rewrite as, and why they wrote it like this, I'm not absolutely certain. Okay, but there's your first derivative. I would have just said minus 12x times x squared plus 3 to the minus 2. So they rewrote it that way. Okay? Then they did the quotient rule here. I would have continued the other one and done the product rule again, or done the product rule for the first time there. They did the quotient rule, fine, it works out, and they got the same thing we did. Exactly. They just skipped a whole lot of steps and got the same thing we did. Okay? Now, what you have to do is analyze this. Where is this positive? Where is it negative? Well, 36 is positive and the denominator is positive. Everywhere. Okay? So that means the only thing that's going to make this negative is this thing right here. That's negative only when x squared is less than 1. In other words, x is between plus or minus 1. Minus 1 and plus 1. That's going to make this negative. There it will be negative. Anywhere outside of that x. Less than negative 1 or greater than positive 1, those will be positive. Because x double prime equal to 0 at plus or minus 1, and that's the only place it is, f prime is defined on the real number line. You should test f double prime on the intervals negative infinity to negative 1, minus 1 to 1, and positive 1 to infinity. We did. I mean, well, no, we haven't tested it, but we showed that it's positive out there, negative in between, and positive over there. So why test? I don't know. We've already shown that to be the case. Okay? Or thought through it anyway. Okay. So the results are here. They get x equal negative 2. They plug that into your form that you had before and find out sure enough that's positive. Concave upward there. Concave upward there. Okay? From minus 1 to 1, negative, concave downward. They chose x equals 0. Very easy to test there. We already saw that was. And then x equal 2, which is outside of 1, concave up again. So here's concave up to here, concave down there, concave up again there. This, by the way, goes all the way to infinity, never touches the x-axis. So it has to be concave up to keep from curving down there. Curving up always. Okay, concave down. All right, any questions about that? The function given in example 1 is continuous on the entire real number line. When there are x values for which the function is not continuous, those values should be used along with the points of where f double prime is 0 or f double prime does not exist to form the test intervals. Okay? It's just that those places where the function doesn't exist, is not continuous, that's not a critical point, okay? It's just not a critical point. But it's also used, just like in that last one, where x wasn't, a little bit earlier. X was not defined at 0, so you do your critical point at -1, do something to the left, between -1 and 0, because you can't use 0, and between 0 and +1, because you can't use 0. You have to treat that as another boundary that you do test interval. Same thing we did before. Now, that was example 1. They're not doing, not doing example 2. So let's go back and do example 2. All right, we'll do example 2 here. Oh, man. Determine the open integrals on the graph of this function. F of x is equal to x squared plus 1 over x squared minus 4. Okay? And determine the open intervals on which that is concave up or concave down. Okay. Before you do anything else, guess what you do first?
See if it's concave up right now.
Okay, yeah, that's our ultimate thing. But before we even get to that,
If it's continuous.
second,
If it's continuous.
set that equal to 0. Is that what you said?
No, but
Okay, what did you mean?
continuous. See if it's continuous.
Is that what?
See if it's continuous.
See if it's continuous. Excellent, excellent. How do you do that? Yes, you do. What is going to mess you up in a function that looks like that? What's the only problem
Two's
with
going to mess you up.
What's that?
Two.
What about 2?
It's going to mess you up.
It certainly will. Is that the only place?
-2.
-2, okay? What I was getting at, here's what's going to mess you up. You have a variable in the denominator. That denominator can never be 0. That is number one thing to check for. If you have a variable in the denominator, make sure that denominator will never be equal to 0. Any place it's equal to 0, that will mess you up, okay? Now, if you also have a variable under a square root or any even root, that can't be negative. That's the second place that could mess you up. If you have a variable inside a natural logarithm, or really any logarithm, you can't be 0 or negative inside, as argument of the logarithm. So in this one, the only thing you worry about is that denominator. And sure enough, that x squared minus 4 cannot equal 0. The denominator x squared minus 4 cannot equal to 0. And then, as you wisely pointed out, x cannot equal plus or minus 2. Okay. Those are not critical values. They're just places the function can't go. Okay. That said, how would you proceed? Take a derivative. Very good. And f prime of x would then be what?
It would be x squared minus 4 times 2x minus x squared plus 1 minus 2x over x squared minus 4 squared.
Okay, I hope that's what you said, right? All right. That's your first group. Now, think it would behoove us, whatever that means, to simplify that, especially that numerator a little bit. Okay? How would you do so?
You get rid of the 2x cubes.
Okay.
I'll multiply that through. You get.
Oh, okay. That's a perfectly fine way to do it.
You get 2x cubed minus 8x minus 2x cubed.
Okay. He's distributing the things you can distribute. That's 2x cubed minus 8x minus 2x cubed minus 2x over x squared minus 4 squared. Okay? 2x cubed minus 2x cubed is 0. That leaves you with minus 10x over x squared minus 4 squared. Okay, good first step. What do you do now? Take his second derivative of f with respect to x. And what does that give you?
You get.
Second?
It's going to be x squared minus 4 squared times negative 10 minus, and you got a chain rule, so it's going to be 2.
Okay.
C's. No, we get to fx. It's going to be minus 10x. And then you do 2 in front of x squared minus 4. Times 2x.
Oops.
2x.
I know, I don't know why I put a square there. Thinking of my parentheses and it came out a square. Okay. Over
X squared minus 4
to the what?
to the 4.
Fourth. Got it. Okay. And now notice what you can do, which you noticed before.
I'm not sure what it is.
Okay. But before you get too far along, don't you see you can get rid of 1 x squared minus 4?
Yeah.
Okay. All right. Now, let's see what we got. Looks like a minus 10x squared plus 40. That's from the first term. And then you got a minus times a minus, which is a plus. And you got 2 times 2x is 4x times 10x is 40x squared. That looks like all you got there, right? Over x squared minus 4 cubed, which is 30x squared plus 40 over x squared minus 4 cubed. All right. Now, there's your second derivative. Said determine the open intervals on which this graph of this function that we had at the very beginning is concave up and concave down. In this case, okay, and remember, x can't be plus or minus 2. Couldn't up there, can't up here. Okay. Now, what we got here is a situation where your numerator is always positive, right? So that's not going to affect the sign of the concavity at all. What you got down here is where your denominator can change signs. Now, as long as x is greater than 2, that's going to be positive, right? And as long as x is less than a minus 2, that will be positive, right? So it looks like to me everywhere left of -2, you're going to be concave up. Right of +2, you're going to be concave up. But when you're between -2 and 2, you're going to be concave down. Because, say, there's a place like 0, that's going to be negative here, that's always positive there. So you're concave down in between. So basically, you don't have anything new to consider. This is never 0, okay? You don't have any other undefined second derivatives except what you had undefined at the very beginning. So there's nothing new here to consider except where you are. So it looks like to me, it says where it's concave up. I'm going to put CC up. U is on the interval from -infinity to -2, and from 2 to +infinity, and concave down. Yeah, I'm going to do it like that on the interval from -2 to 2. Notice we definitely use open intervals here. You cannot include either one of those on it. So don't, okay. So concave up on these two, concave down. Okay. Now, they didn't ask this. Should I? Why not? Where do you have a critical point? Okay? If you look at this first derivative, the only place where it is equal to 0 is the x equals 0. Well, that's on this interval here. That's concave down, so that's going to be a relative maximum. Right there, you can tell. X equals 0, critical point, and it's in this interval where it's concave down, so that's a relative maximum. Okay? The other places, no, the outside, the 2's, no relative maximum, no relative minimum, because that's the only place where that is. Now, where the first derivative doesn't exist, the only places are where the function doesn't exist. So don't count those as critical values. Only critical value is x equals 0. That's on that interval. That's where it's concave down, so that'll be a relative maximum. Does that make sense? That was more than the problem asked for, but we got it. Okay? Now, excuse me. They do the test for concavity. I'm not doing the test. In a sense, I sort of am. I'm saying, where is it positive and negative? Looking at the function, where is it positive and negative? And that's determining it. They like to actually pick points and plug them in. Whichever you prefer, you can do. But just get points outside your other. So they had it concave up. Outside of below -2, we did too. Concave down, inside, we had it too. And concave up again, outside, and there you have it. And here's what that function looks like. This wouldn't be too hard to graph, but it's concave up over here, but no relative minimum or maximum, because it's just constantly increasing here, constantly decreasing there, so it's concave up again there, concave down here with the relative maximum, which you got from the first derivative. Okay. And it's not at 0, 0, it's at -1/16. Okay, I think is what that is. For it's close to 0, but not quite. Okay. Any questions? And again, if you can look at the function and reason it out where it's concave up and down, that's fine. If you'd rather not do that and just plug in points, just pick a point, left, right, and in between each of the other 2 points. They don't have to be critical points. They can be points where they're not defined or critical points. Any questions? All right. Then we're ready for points of inflection. Okay? Yeah, I was just looking to see how far I thought we could get. If the tangent line to the graph exists, now what does that mean? If the tangent line to the graph exists, that means the first derivative is defined there. Tangent line, first derivative. Think of those together. Tangent line to a graph exists at such a point where the concavity changes. If the tangent line exists at the point where the concavity changes, then that is a point of inflection. Okay? Now, there's one of three situations they describe them here. Here you're concave up, and here you're concave down. If the tangent line exists at that point where the concavity changes, then that's a point of inflection. Okay? It went from concave up to concave down. It could have gone the other way. That would have still been fine. Here's another one that we've run into before. Concave up here, and concave down here, concave up here. There's your point of inflection. Okay? Now notice here. Here your tangent line was not 0, but you had a point of inflection. Here the tangent line is 0, and you had a point of inflection. Now this will be, I think, the one and only one case where you have a first derivative equal to 0 that you do not have a relative extremum. It has, if it's not a relative extremum, it's going to be a point of inflection. That doesn't mean every point of inflection will be a horizontal tangent. This shows it's not. But here's the other one. This will be the real problem child. Concave up here, concave down here, change right here. Guess what happened here? Yeah, your first derivative did not exist. It's a vertical tangent line. Okay? But it has to be a tangent line at the point where the concavity changes. That's the point of inflection. Okay? Now, here's the other thing they say. Note that the graph of the function crosses the tangent line in all three cases here. If the tangent line was strictly on the upside or downside, then you wouldn't have a point of inflection. You'd have a relative minimum or maximum. Okay? But if the graph crosses the tangent line, that is another indicator you have a point of inflection. So on a graph, that's a way to look.
So basically, inflection points is just where it changes from concave up to concave down.
Say this one more time.
Inflection point where it changes
from concave up to concave down. Exactly. That's it's sort of the shorthand way of saying this. If a tangent line exists at a point where the concavity changes, then the point is a point of inflection. So if the concavity changes, it's a point of inflection. You're right. Okay. And I think that's all we have time for. Is that right?
10:38.
Huh?
10:38. Yes.
Okay. So let's start at this graph, this plot next time. Definition of a point of inflection. Oh man.
What's wrong?
No, we did. Okay, I'm sorry. Here we go. Oh, we had already done example 2. I was on the wrong thing. So we'll pick up there, bottom of page 193. Did we get enough for a few homework exercises here? I think so. I think you can do number 3. And I think you can do any of the odds 5 through 15. They're all at calcchat.com. 13's at calcview. And we'll hold off doing finding the points of inflection. Okay? So just go through 15. Good deal. Any questions? All right. We'll sadly not see you on Wednesday. Okay? Now, if you want to show up, have class without me, I won't be here. But, enjoy. But we'll pick up with there next month. All right. Good deal. Have a good 4th.
You too.
Thank you. Now, of course, to have a good 4th, you'll be working on your papers and the test. That'll make it good, won't it? Absolutely. Good deal.